In this video, let us try to solve some of the problems in shear force and bending moment diagram. Here is a beam with some loads like 20 kilonewton point load and 2 kilonewton meter counterclockwise moment, and 4 meter is the length of the beam, and this 2 kilonewton meter moment is acting in the middle, that is at 2 meters from one end. Now we want to draw the shear force and bending moment for this loading diagram. Okay, and let us start with the shear force diagram. This is the reference line, and we have 20 kilonewton load here. Okay, due to this load, this part of the beam is bending like this, right? Bending like this. On this beam, if I consider any element on this beam, actually I'm drawing here as a line diagram. It could have some cross section of the beam. Okay, and this element is subjected to load like this, right face downward, left face upward. This kind of element is said to be a positive shear force. If the element right face is subjected to downward force, that is said to be the positive shear force. Okay, so we are starting the shear force diagram here, and since this is the positive shear force, we are drawing one line of same magnitude, whatever is there, 20 kilonewton. We are drawing that 20 kilonewton load. Okay, and since there is no load till this point, this 20 kilonewton will continue till this part. This is a straight line and it is a constant. Okay, and this is the positive shear force diagram. Our shear force diagram is nothing but a rectangle in this case. Okay, now let us try to draw the bending moment diagram for this. We are drawing one line here. Okay, since this load is bending like this beam is bending, and this load is causing hogging bending moment. This is called hogging bending moment, and it is said to be negative. Okay, so we have to draw on the bottom side of the reference line. While drawing the bending moment diagram, we should draw on the bottom side of the reference line. Okay, at this location our bending moment is 20 into 2 meters, that is 20 into 2 meters, 20 kilonewton into 2 meters, which is 40 kilonewton meter. And at this location our bending moment is 0, because the load itself is passing through that point and there is no distance is 0 in this case, and our bending moment is also 0 at this end. And So our bending moment diagram will be like this. This is a straight line actually. Since there is a constant line here, we should get an inclined line here, always 1 degree extra. Okay, this one we are this is a straight line. Okay, and wherever there is a movement, we should get a vertical line in the bending moment diagram. So here is our 40 kilonewton meter load is there, 40 kilonewton meter, and this 20 kilonewton meter is causing a clockwise moment, while we have this 2 kilonewton meter is a counterclockwise moment. So its nature is opposite compared to this 20 kilonewton meter, compared to this 40 kilonewton meter. So we have to go up by an amount 2. Okay, here if we go up by an amount 2, we are at 38 kilonewton meter, right? And at this location our bending moment is nothing but at the end of the beam where it is fixed, our bending moment is nothing but 20 into 4 meters, that is 40 20 into 4, that is 80, which is a clockwise moment, while we have another moment is there which is counterclockwise moment, that is minus 2 kilonewton meter, which will comes to be 78 kilonewton meter. So this is 78 is the bending moment at this location. So we are just drawing a straight line and we are joining these two by another straight line. This everything is a negative bending moment since it is hogging. Okay, this completes the shear force and the bending moment diagram for this. And if we want to draw the shear free body diagram for this beam, I'll just try to draw here. Just place the loads as it is. The load here is this 2 kilonewton load is there, and we have one more load in the middle, that is 2 kilonewton meter moment. Here is our 2 kilonewton meter moment. Kilonewton meter, and we know that this beam is in equilibrium. So there is a total load of 20 kilonewton here from the top, 20 kilonewton from the top. So to have a balance, we need to have upward force of the same magnitude here also. Here is our 20 kilonewton. Okay, in this case the force is balanced completely. Upward force must be equal to the downward force, that is 20 kilonewton must be equal to the 20 kilonewton here, but not the moment is not balanced in this case. If we see the moment at this location at the end, 20 kilonewton into 4, that is 80 kilonewton. A clockwise moment is there, and 2 kilonewton counterclockwise moment is there. So the dominant moment is clockwise moment, that is 78 kilonewton meter. So to arrest that moment, we are adding one more counterclockwise moment of the same magnitude, that is 78 kilonewton meter. This is the free body diagram for this loading diagram. So if you observe in this case, wherever there is a force, there you are getting a vertical line of the same magnitude. Here you have 20 kilonewton, and in the shear force diagram you have the same 20 kilonewton vertical line is there, and here you have 20 kilonewton force is there, and here we have 20 kilonewton vertical line is there. And coming to the bending moment diagram, we have two bending moments here in the free body diagram, that is 2 kilonewton here in the middle and 78 kilonewton meter at the end. So we have the same things here also. In the bending moment diagram, we have in the middle 2 kilonewton meter vertical line is there. Similarly, we have 78 kilonewton meter vertical line is there at the end. Let us consider one more example of simply supported beam which is carrying 40 newtons load, 40 newtons per meter load here, 40 newtons per meter load here. Okay, now we want to draw the shear force and bending moment diagram for this. Whenever there is a simply supported beam, the first step is to find out the reactions. Let us say the reactions are RA and RB. The total load coming from the top is 40 Newton per meter load intensity is there, and it is acting over a length of 1 meter. So the total load coming from the top is 40 newtons, and into length is 1 meter, which is 40 newtons itself. 40 newtons must be equal to this total load coming from the bottom, that is RA plus RB. RA plus RB. Now let us try to take moments about this point. Actually, we can take moments about any point to have other equation, that is to have moment equilibrium. Let us consider this point A, and let us say this is point B, and the sum of the moments about the point A must be 0. That is, at point A, this RB is causing a counterclockwise moment. So RB into the distance, total distance is 4 meters here in this case, must be equal to the total moment by this load, that is total load of the UDL is 40 newtons, and it is acting at the center of gravity of this point, center of gravity of the UDL, that is the middle of the UDL. So the distance from here to the point A is 2.5. So our RA will become, sorry, RB will become 25 newtons. If RB is 25, RA must be 15 using this equation. So RA is 15 here, 15 newtons, and RB is 40 newtons. Now we can draw the shear force diagram for this, and this RA 15 Newton is causing deflection like this in this case. So the element is subjected to this kind of load. Okay, right face downward, which is considered to be positive. So this is the reference line of the shear force diagram. At this RA I am going up by an amount 15 newtons, and till here at this location, till this location there is no load. So I will continue till this part, till this location. Okay, and its load is just opposite in nature compared to this RA, because RA is acting upward and this load is acting in downward direction. So, and this load is causing a total load of 40 newtons is there, and it is varying across this. I'm drawing this line in the downward direction because due to this load we are going up, and due to the load from the top we should go down, and it is varying. It is causing a total load of 40 newtons over a span of 1 meter. Okay, and this will continue as it is till here. Okay, and this must be 25 newtons. Here we got in the negative direction. It is due to this RB, our element is deflecting like this. Our beam is deflecting like this. So the element is subjected to this kind of load. Right face upward, which is considered to be negative. So this is negative. Sorry, here RB is not 40 newtons, it is 25 newtons. Now let us try to draw the bending moment diagram. The bending moment at this point is 0, that at point A, because the load itself is passing through that point, and due to RA the beam is bending like this, which is a sagging. Sagging is considered to be positive, so I'm drawing on the positive side of this reference line. At this location, that is at this location, the bending moment is nothing but RA into 2, that is 15 newtons into 2, that is 30 Newton meter. 30 Newton meter. At this location is nothing but 30 Newton meter, and at this location we have 25 Newton meter. So I'm drawing a bit lower here. Okay, these two are straight lines. This is a straight line. This is also a straight line. Okay, and if there is a straight line, that is a constant line in the shear force diagram, we are getting inclined line. A straight line is there and inclined line is there, always 1 degree extra. It goes like this. The first if the shear force diagram have a constant line like this, our bending moment diagram will have an inclined line. Our shear force diagram, if our shear force diagram has this inclined line, our bending moment diagram will have parabola. If our shear force diagram has a parabola, our bending moment diagram will have a cuboid. That means it will have even more curvature compared to the parabola. Here I'm writing like this is straight line, that is constant line, actually constant line. Here just as this, here is a constant, right? The shear force is constant, and we have this is inclined line or uniformly varying line, inclined line anyway it is. And here is the parabola. Here it is the parabola, and this one is cuboid. Okay, and since we have a inclined line in the shear force diagram, we should have a parabola. So I need to join these 2 points by a parabola like this. Okay, and if I find out the slope of these curves, I should get the shear force diagram. For example, the slope here in this case is nothing but this total height, which is 30 by 2 meters, right? So it is 15, that is matching with the shear force diagram. For example, if I want to find out the slope here, the slope here is nothing but this total height, which is 25 Newton meter, right? 25 Newton meter, just 25 Newton meter, and this one by this much, this is 1 meter, which is 25 itself. That is where we are. And lines like this will have positive slopes. Lines like this will have positive slopes, and like lines like this will have lines like this will have negative slope. And lines like this will have negative slopes.